Today's chemistry lesson is about
Dalton's law of partial pressure and gas stoichiometry. Our objectives for this lesson are to
use Dalton's law of partial pressures to relate mole fractions and partial pressure of gases in a mixture.
Apply the principles of stoichiometry to determine the amounts, volume, number of moles or mass of gaseous reactants and products.
Raven Naninipot, Jewel Esperas, Elvin Reve, Katrina Iglesia, Antoinette Ortiz, and Pauline Anshoho will be teaching and help you understand the topic.
First, I will be giving you an introduction to what Dalton's law of partial pressure is. Are you ready?
Yes!
Dalton's law of partial pressures is a gas law that states that the total pressure exerted by a mixture of gases is equal to the sum of the partial pressures exerted by each individual gas in the mixture. The total pressure exerted by a mixture of gases is the sum of the partial pressures of component gases. Dalton's law of partial pressures can also be mathematically expressed as follows, where P total is the total pressure and the other terms are the partial pressures of the individual gases, depending on the number of component gases. So, what is partial pressure? It's the pressure exerted by an individual gas in a mixture. It can be expressed in torr, millimeters of mercury, or atmospheres like any other gas pressure. The partial pressure of each gas in a mixture is proportional to its mole fraction. On the other hand, we use the ideal gas law to determine the partial pressure of a certain gas in the mixture. The ideal gas law assumes that all gases behave identically and that their behavior is independent of attractive and repulsive forces. If volume and temperature are held constant, the ideal gas equation can be rearranged to show that the pressure of a sample of gas is directly proportional to the number of moles of the gas present. P stands for the absolute pressure of a gas. V is the volume it occupies. N is the number of atoms and molecules in the gas or amount of substance. T is its absolute temperature. And the ideal gas constant that stands as R is 0.08206. In calculating partial pressure, a sample of gas A evaporates over water in a closed system. What is the pressure of gas A if the total pressure is 780 torr and water vapor pressure is 1 atmospheric pressure? First, we convert the pressure to the same units. To convert the pressure, we divide 780 torr to 760 to get the atmospheric pressure, 1.03. Then, after that, we subtract water vapor pressure from total pressure to get partial pressure of gas A.
Allow me to explain and give you examples in calculating partial and total pressure. To find the total pressure, we must apply the previous steps to get the pressure of each gas. Here we are asked to calculate the total pressure of a mixture that contains 2.5 grams of helium and 5 grams of argon in a 7-liter container at 20 degrees Celsius. So we first have to convert the grams of helium and argon to moles. 2.5 grams of helium then becomes 0.625 mole and 5 grams of argon becomes 0.125 mole. Then convert the given temperature to Kelvin, which is equals to 293 Kelvin. Now that we have converted the grams to moles and changed the temperature to Kelvin, we compute the two mixtures using ideal gas law. Using the formula nRT over V, or 0.625 mole times 0.0821 atm times L per mole times 293 Kelvin divided by 7 liters. Compute that and we get 2.14 atm. And then we can do the same for argon, which is 0.125 mole times 0.0821 atm times L per mole times 293 Kelvin divided by 7 liters. Now that we have the pressure of helium and argon, we can then get the total pressure by adding 2.14 atm plus 0.429 atm, which we then get 2.57 atm. One container with 24 liters of nitrogen gas at 2 atm and another container with 12 liters of oxygen gas at 2 atm. The temperature of both gases is 273 Kelvin. If both gases are mixed in a 10-liter container, what are the partial pressures of nitrogen and oxygen in the resulting mixture, and what is the total pressure? We are first asked to find the partial pressures of nitrogen and oxygen. To find these, we will be using the formula N equals to PV over RT, which is pressure times the given volume divided by the gas constant times the given temperature. For nitrogen gas, 2 atm times 24 liters divided by 0.0821 atm times L per mole times 273 Kelvin, which is equals to 2.14 mole. And for oxygen gas, 2 atm times 12 liters divided by 0.0821 atm times L per mole times 273 Kelvin, which equals to 1.07 mole. We now have the partial pressures of nitrogen and oxygen, which means that we can now get the total pressure. We will be using the formula P equals to nRT over V, which means that we will have to multiply the mole by the gas constant times the temperature divided by the volume. For nitrogen, 2.14 mole times 0.08206 atm times L per mole times 273 Kelvin divided by 10 liters is equals to 4.79 atm. And then for oxygen gas, 1.07 mole times 0.08206 atm times L per mole times 273 Kelvin divided by 10 liters equals to 2.40 atm. Then we can get the total pressure or the P total by adding 4.79 atm plus 2.40 atm, which means that the total pressure or the P total in the mixture is 7.19 atm. Let's proceed with mole fractions of gas mixture.
Mole fractions of gas mixtures. The composition of a gas mixture can be described by the mole fractions of the gases present. The mole fraction X of any component of a mixture is the ratio of the number of moles of the component to the total number of moles of all the species present in the mixture. So the equation for mole fractions is equal to the moles of A divided by the total moles.
Calculating mole fraction and partial pressures. In this sample problem, we have to calculate the total pressure inside the 10-liter container, as well as the partial pressure of A and partial pressure of B. We first have to identify the given for gas A and for gas B. For gas A, the temperature is 300 Kelvin, the volume is 30 liters, and the pressure is 1 atm. For gas B, the temperature is 300 Kelvin, the volume is 15 liters, and the pressure is 2 atm. Before we can calculate the total pressure, we first have to get the number of moles of gas A and gas B. So, using the ideal gas law equation PV over RT, we can get from gas A 180 times 30 liters divided by the gas constant, which is 0.08206 liters atm over mole K times 300 K equals 1.22 moles. And for gas B, the number of moles is 2 atm times 15 liters divided by the gas constant 0.08206 liters atm over mole K times 300 K equals 1.22 moles. And we get the total number of moles by adding the two, which is equal to 2.44 moles. To get the total pressure, we can use the ideal gas law equation. The total pressure is equal to the number of moles times R times T divided by V. So that's 2.44 moles times constant 0.08206 liters atm over mole K times 300K divided by 10 liters equals 6.06 atm. So since we know that partial pressure is equal to the mole fraction times the total pressure, we first have to get the mole fraction for gas A and for gas B. So that's number of moles divided by the total number of moles. So that's 1.22 divided by 2.44 equals 0.5. And that's for gas A. And 1.22 divided by 2.44 equals 0.5. And that's the for gas B. So after getting the mole fraction, you can use it to get the partial pressure. So the mole fraction times the total pressure, that's 0.5 times 6.006 atm, which equals 3.003 atm, and that's for gas A and gas B.
Now let's learn about gas stoichiometry to determine the volume, number of moles, and the mass of gaseous reactants and products.
Gas stoichiometry. Gas stoichiometry is the study of the relative amounts of reactants and products in reactions that involve gases where their temperature, pressure, and volume are known and can be assumed to be ideal gas. Using stoichiometry calculations, we can convert between mass, the number of moles, and the volume of gases. While standard temperature and pressure, or STP, is when standard temperature is at 0 degrees Celsius or 273 Kelvin and the standard pressure is at 1 atmospheric pressure. Please remember that at STP, 1 mole of gas is equal to 22.4 liters, and you can use this to convert moles to liters and liters to moles. But when the gas is not at STP, we use conversion factors and the ideal gas law to determine the missing values, like the volume, number of moles, and mass. Now, there are 3 types of gas stoichiometry problems: mole to volume, or volume to mole, mass to volume, or volume to mass, and volume to volume.
There are 2 ways to find the volume with moles depending on whether or not the temperature and pressure are stated. Let's have this example. What is the volume of 2.5 moles of argon gas at STP? Since we are given 2.5 moles of argon gas at STP, or at 273 Kelvin and 1 atmospheric pressure, we can use 22.4 liters to determine the volume. So, 2.5 moles of argon times 22.4 liters divided by 1 mole of argon is equal to 56 liters. This is now our final answer. Let's try another example. How many liters of ammonia can be produced at a temperature of 27 degrees Celsius and a pressure of 760 torr if 20 moles of nitrogen gas are consumed? In this chemical equation, we are asked to find the volume of ammonia in liters. By the way, before solving, make sure that the chemical equation is balanced. Let's state what is given. So, the temperature is 27 degrees Celsius. We have to convert it to Kelvin by adding 273. So that is equal to 300 Kelvin. Our pressure is 760 torr. To convert it to atm, we divide it by 760. So that is equal to 1 atm. The N, or the amount of moles of nitrogen gas, is 20 moles. And we are looking for the volume of ammonia in liters. So first we have to determine N, or the amount of moles of ammonia from the given mole of nitrogen gas. So 2 moles of nitrogen gas times 2 moles of ammonia divided by 1 mole of nitrogen gas is equal to 40 moles of ammonia. We got 2 moles of ammonia from the coefficient of ammonia in the chemical equation. Now that we have the moles of ammonia, we can use the ideal gas law equation to solve for the volume in liters. So that's PV is equal to nRT. So substitute the values. We have 1 atm times volume equals to 40 moles times 0.08206 liters times atm over mole times K times 300 Kelvin. Divide both sides by 1 atm and cancel all units except liters since we are solving for volume. So if we compute that, we get 984.72 liters of ammonia. We can also get the same answer if we rearrange the ideal gas law equation to P equals nRT over V. I'll let Elvin explain the other types of gas stoichiometry problems.
Mass to volume. In solving for the volumetric mass, we have to find the mole of the unknown first with the given mass using conversion factors. For example, how many liters of hydrogen gas will be required at a temperature of 300 Kelvin and 3 atmospheric pressure to consume 56 grams of nitrogen gas? So we are given a temperature of 300 Kelvin, 3 units atmospheric pressure, and the mass of 56 grams of nitrogen gas. In the equation, we are asked to determine the volume of hydrogen gas. In order to solve this, we have to convert 56 grams of nitrogen gas to moles of nitrogen gas to moles of hydrogen gas. So we have 56 grams of nitrogen gas. Per 1 mole of nitrogen gas, there are 28 grams of nitrogen gas. This gives us with 2 moles of nitrogen gas. And per 3 moles of hydrogen gas, there is 1 mole of nitrogen gas. This leaves us with 6 moles of hydrogen gas. After finding the moles of hydrogen gas, we can now convert it to liters. Since it is not at STP or standard temperature and pressure, we can use the ideal gas law to find the volume. So 3 atmospheric pressure times volume is equals to 6 moles of hydrogen gas times 0.08206 liters atm over mole K times 300 Kelvin over 3 atm. So now we have 49.2 liters of hydrogen gas. Volume to volume. Among the other types of gas stoichiometry problems, this is the easiest type since according to the law of combining gas volumes, gases combine at the same temperature and pressure in a simple whole number of volumes. This means you can use the coefficient in a balance equation to form a volume-to-volume relationship. Let's have this example. How many liters of oxygen gas will react with 5.0 liters of hydrogen gas to form water? Since small ratios are also volume ratios, we can use the coefficients of the necessary reactants or products from the chemical equation to determine the volume. So 5.0 liters of hydrogen gas. Per 1 liter of oxygen gas, there are 2 liters of hydrogen gas. This leaves us with 8.5 liters of oxygen gas. Things to keep in mind. First, stoichiometry calculations or conversion factors can help in the conversion between volume, number of moles, and mass of a gas. Second, we can use 22.4 liters to convert volume to mole and vice versa when at STP. Third, list the given first so that you can easily calculate what is being asked. Fourth, always make sure that the chemical equation is balanced. 5. Always determine the moles first in order to find the volume or mass of a gas.